This is a problem that has to do with the relationship between the surface area of a sphere and the radius of the sphere. You can see that if you were to change the radius of the sphere, then the surface area would have to change it as well, because there's this relationship that always has to be true between the two. So because this relationship always has to hold, that's going to determine a relationship between the rate at which the radius changes and the rate at which the surface area changes as a function of time. So we're looking for how are not just the two quantities, the surface area and the radius, related, but how are the rates of change related. So we're talking about related rates here. Well, the way to figure that out is to assume that both of these functions depend on time. So we could take the derivative of this equation on both sides with respect to time. So when I do that, assuming that s is a function of time, on the left-hand side we get ds dt. On the right-hand side, the 4 pi is a constant, and then we take the derivative of r, which we're assuming is a function of t, so by the chain rule the 2 will come down, we'll get r to 1 power less, and then we'll have to multiply by the derivative of what's inside, the dr dt. So we end up here with a relationship between the rate of change at which the surface area changes and the rate of change at which the radius changes. So see how we have related rates. One rate is related to the other rate in some particular way. Now this is kind of interesting. So imagine that you were changing this radius at a constant rate. What would happen to the surface area? Well, when the radius is small, ds dt would be small. So even though you're increasing the rate, the surface area isn't increasing very much when the radius is small. But when the radius starts to get big, then this big number multiplies the rate at which the radius is changing, and so you see that ds dt is actually bigger when the radius itself is bigger. So they don't change lockstep, but they do have a relationship, and that's what we're interested in, is how are the two rates of change related. Okay, here's just an example where we have some variables. We're going to assume that x and y are two numbers that can change with time, and we just want to know how is the rate of change of x related to the rate of change of y. Well, since this equation is assumed to always hold true, we just take the derivative of both sides with respect to time. Now 12 is a constant, so it can't change, so its rate of change is 0. Here we get 2 times dx dt, whatever that might be, and 3 times dy dt. So there's the relationship between the two rates. We want to find dx dt, so what I'm going to do is solve for dx dt by moving this term with dy dt over. Then I can divide both sides by 2, and I get negative 3/2 dy dt. This tells us something about the relationship between these two variables. If dy dt is positive, if y is increasing, then x has got to be decreasing, which kind of makes sense from this relationship, right? The two numbers have to add up to give 12, so if you increase y, then you've got to decrease x to keep that total equal to 12. Or if dy dt is negative, then you have a negative times a negative, so dx dt will be positive. So if you're decreasing y, then you can increase x. This just, from the relationship that always has to hold true, we see a relationship between the rates of change. Now in this problem they tell us that dy dt is negative 2, and they ask us to figure out what is dx dt then. So if dy dt is negative 2, we could just plug that in, right? And let's see, negative 2 times negative 3/2 would be 3, so we see that dx dt is 3. So if we're decreasing y at a rate of negative 2 units per time unit, then dx dt will increase by 3 units per time unit. So we have our relationship there. Okay, let's do a couple more here. Here x and y are related quantities, and we know how y is changing, and we want to know then how will x be changing. So if we take the derivative of both sides with respect to x, on the left we get dx, or with respect to t, sorry, both are assumed to be changing with respect to some other variable t, like think about it as time, so that it's a time rate of change. Let's see, if we take the derivative of y cubed, we would get 3y squared times the derivative of y with respect to t. and then we subtract dy dt. Okay, and the question is about what is dx dt if we know that y is 2 and dy dt is 5. We just plug those given numbers in to figure out what's the rate of change of x with time. So they told us that y was 2 and dy dt was 5. So we get here, let's see, 4 times 3 is 12, 5 times 12 is 60, 60 minus 5 is 55. So because of this relationship that exists between x and y, then when dy dt is 5 and y happens to be 2, then dx dt is going to be 55. Okay. Another one. Let's see. Here we have a relationship between x and y. They tell us the rate of change for y, and they want us to find the rate of change of x with respect to t. So again, we just differentiate both sides of our relationship with respect to t. Okay, so first we have a product of two functions. So we take the derivative of the first, which would be 2x dx dt, times the second, which is y cubed, plus the first, which is x squared, times the derivative of the second, which would be 3y squared dy dt. Now over on the left-hand side, we have the derivative with respect to time of some constant 4/27, and so we get 0. Now we're told what dy dt is, and we want to find dx dt, so what I'm going to do is I'm going to try to get this dx dt alone. First thing I'll do is move this other term over. So I have negative x squared 3 times y squared dy dt. Next thing I'll do is to divide by 2x and y cubed. So that will give me dx dt alone, and then I'll have negative x squared 3y squared. I'm dividing by 2xy cubed dy dt. Now we can see the relationship between those two rates. If I simplify a little bit, let's see, this x cancels one of those. These two y's wipe out all but one of those. And so we have negative 3, what's left on top, 3x over 2y dy dt. Okay, so for this particular relationship, we can see, let's assume that x and y are both positive numbers. If that's the case, then if you start increasing y, so dy dt is positive, then you'll have dx dt is some negative number. So you'll see that increasing y requires you to decrease x. Okay, so they ask us now a particular question. What if at some particular time dy dt is 1/2 and x happens to be 2? So then I could go this far. I know that x is 2, so we're going to have negative 6 over 2y, and dy dt, they tell me, is 1/2. Ooh, but I need to know what's y. Well, I can get that from the original relationship. They told me that x was 2, so if x is 2 at some particular time, then x squared will be 4, so 4y cubed will be 4/27. Just multiply both sides by 1/4, and you'll see that y cubed is 1/27. And we can take the cube root. 1/27 is 1/3 times 1/3 times 1/3, and so y must be 1/3. So now I can get a specific value here for dx dt. We have, let's see, 3, so negative 3 over 1/3. There's also a 2 downstairs here. So I have a complex fraction. I'm just going to multiply top and bottom by something that tiny denominator can go into, which is 3. So when I do that, I get that dx dt is, let's see, this 3 cancels that one, and 3 times 3 is 9, so negative 9/2. So we find that at this particular instant, when x is 2 and y is 1/3, and you start changing y at a rate of 1/2 unit per time unit, then the x will start decreasing at a rate of 9/2 a unit per time unit. All right, one more, and we'll move on to maybe some more applied problems. Okay, here we have three quantities. There's r, there's s, and there's v, and this particular combination of the three always has to add up to be 12. So if we know the rate at which r is changing and the rate at which s is changing, and maybe a little bit about what their current values are at some particular instant, then we can find the rate of change of v at that particular instant. Again, we just have a relationship that's assumed to always be true, and we differentiate it with respect to time. So I take the derivative with respect to time on both sides. So the derivative of a constant with respect to time is 0. And over on this side, we'll get dr dt, and then we have a function of t squared, so by the generalized power rule, the power comes down, you get s to 1 power less times ds dt. And here you have a function of t cubed, so the 3 comes down, you get the function of 1 power less times dv dt. So here we have a relationship between these three. Now, we're told what the value of dr dt is, right? We're told that that's 4, and we're told that the value of s is 1, so, and that the value of ds dt is negative 3. So we have 2 times 1 times negative 3 for this, and then we have 3v squared and dv dt, and that's all equal to 0. I can almost get dv dt, that's what they asked me for, but I need to know what v is. To do that, I could use the original equation. So I'm told that at this particular instant, r is 3 and s is 1, so we have 3 plus 1 squared plus v cubed equals 12. So let me subtract 4 from both sides so that I get v cubed alone. Okay, and now I can see v cubed is 8, so v must be the cube root of that, which is 2. So 2 squared would be 4, so I have 4, this is minus 6, and then we have 3 times 4 is 12 dv dt. Now I can solve for dv dt. These guys are negative 2 plus 12 dv dt. Let's move the negative 2 over, so we would have 12 dv dt. Oh, this is equal to 0, sorry. So we'd have 12 dv dt equals 2. So dv dt would be 2 divided by 12, which is better known as 1 divided by 6.